Hey, everybody. Thank you very much for being here. I realize I stand between you and lunch, so great responsibility. I will try to both entertain and educate you as far as I can. So hopefully this is a sort of familiar kind of a picture to many of you. It doesn't really matter whether it's a cluster or you have some large group of instances that you need to manage, and one of the things you have to do with these, of course, is have a way for your services to discover one another and to have those services be available in a highly available way, so you need to do some failure detection. I guess from the demographic there's a chance that you're using HashiCorp technology to do this. Maybe not. We like to play nicely. You don't have to use all of our tools. But Consul, of course, is one possible solution for doing this. So when you decide who you're going to put your trust in for your failure detection solution, there's a number of criteria that you use to evaluate the technology that you're going to use. We appreciate that you have many choices in this area. And of course, we also, as HashiCorp, when we were looking to understand the best algorithms that we should use inside of Consul, we also had the criteria that we needed to use to evaluate the right technology. And these are the kind of things, these are general ways that you would evaluate any technology, right? How does it perform? Performance in this context includes several dimensions. What is the latency of how quickly, if there's a failure, how quickly we're going to detect that failure? How quickly will we propagate that failure to everybody in the system? What's the error rate like? Are there going to be false positives? Are there going to be false negatives? How many? And also, in this area, we have a consistency model. We actually offer both. Consul offers a strong consistency model. If you need everybody to be on the same page, then it's possible to go to the Consul servers and to get one definitive view of the health of the system, of the nodes. Or, if you don't need that, you can go with the weaker model. You can use Serf and get something that's more fresh. And then for efficiency, of course, what is the overhead of all of this? What are you going to do to how many messages are you going to send on the network and CPU and memory on the instances where you're running this agent or whatever? And then reliability. I mean, in this particular case, this is a sort of a sensitive subject, because what's the point of having a failure detection mechanism if it itself is not reliable? We need to know when there's a failure, and we can't have this sort of infinite regression of turtles all the way down. The buck stops somewhere, and you want to know that this thing is a reliable system. But also, there's a special criterion. When you're thinking about failure detection, you need to think about the failure model. And you can sort of compare this to the threat model in security. This model here, it's sort of defining the domain. It's the things that are going to be visible to you. What are the semantics? What are the ways that things can fail? So implicitly or not, whether you realize it, you're always shopping based on the failure model of your failure detection system. So luckily, there are many failure modes to choose from. And this is a nice diagram that Stefan Polenda from Technical University of Wien put together. He teaches a great course. By the way, all of the things that I reference, at the end I'll give you my Twitter handle, and I've just tweeted the links to all of these things, so don't be scrambling to write down URLs and things. You can go find all of this stuff afterwards. So yeah, this is, many people actually have referenced Stefan's writing about this. There's a sort of a hierarchy of failure modes here. And we're sort of starting at the outside. We're starting with very general, arbitrary failures. In fact, the definition here of a Byzantine failure is that it's absolutely arbitrary. It could fail in any kind of a way. It doesn't have to stop. And it covers all sorts of horrible things, the sort of malicious and collusion situations where people are actually trying to bring your system down. They're injecting, confusing, malformed messages or conflicting messages. So it's the most general thing that we could try and recover from. And then there's a sort of narrowing down. Each ring here, we're going in, we're making some simplifying assumptions. We're reducing the scope and making it more of a tractable problem. How can we actually implement a failure detector that can find this particular class of failure? And then right in the middle there, you have fail stop. So not only is it crashing, it's inside of crash, so that means it has to have crashed, but it crashes nicely. And I'll come back to this in another couple of slides, actually. So Byzantine fault tolerance, BFT, Byzantine failures were on the outside of that. They were the most general thing. By the way, they come from a related problem, the Byzantine generals problem. This is the guys who are trying to attack, and they have to send messages to each other to coordinate the attack. But of course, one of them might be a bad actor, malicious. He's a spy for the other side. And is there a way to make a protocol that enforces consistency here? And it's actually thinking of it as a consensus problem. Not surprisingly, Leslie Lamport posed the Byzantine generals problem. This is the same person who gave us the Paxos consensus protocol. So great, this thing it's very general. We can handle arbitrary faults. So you'd think this is something that people would aspire to. We should be seeing this out there in the marketplace, right? Well, it turns out it's not widely deployed. And I think you see this for yourself. And I mean, there's no open source project out there that everyone is jumping onto to use this thing. OK, well, maybe you need to be Google, you need to be Microsoft. So Leslie Lamport works at Microsoft, and I'm going to give you the citation later for a paper from Microsoft where they say that it is not being used in a production system inside of Microsoft. In fact, I think they mean generally in the world, but certainly they would know whether it's in Microsoft. And then Google, who leapt on Paxos and made it famous, also are asserting that BFT is not ready for prime time. And there's sensible reasons for this. When you go and look at the BFT class of systems, they're complicated protocols. And they've been simplified, they've been made more tractable, but nevertheless, they're complicated protocols. To tolerate F failures, you typically need 3 F+1 instances, so there's a lot of overhead here. And as a consequence of these things, the way they scale, the number of messages, the number of instances that can be brought in, it's a tough thing to do, which is it pretty much makes sense why this stuff is not widely adopted. And you could say that probably it's overly pessimistic for the data center. We don't have Byzantine generals typically in the data center. You want to do something more lightweight. You want to defend against accidental failures, not somebody being malicious, unless it's something super sensitive. It turns out Bitcoin actually is a great candidate for BFT because everybody is going to try and game the system, and it has to be absolutely rock solid in a fully distributed manner. So BFT, if you go to any of the conferences working on Bitcoin stuff, you're going to see Byzantine fault tolerance is front and center with Bitcoin. So what you do see when you go look at the literature and look at the systems is everyone's really come down to either the crash failure model, which is sometimes called crash stop, and then the fail stop failure model. And the crash just says the thing stops. It no longer will send messages. The only promise you have to make is that this process that we were monitoring disappears. Fail stop is stronger. It requires that it stops in the same way. But this is a model where people are trying to make things actually fail on purpose in a consistent manner because they would like it to leave the system. The remaining nodes, the healthy nodes, should be able to recover the global state of the system. So, clean up after yourself. Be a thoughtful colleague as you go and crash out in flames. So, but these are all simplifying assumptions. The crash failure one seems pretty reasonable, all right? And you'll see many, many papers, many, many concrete implementations asserting that crash failure is their model. They can't go further and promise fail stop, but the crash failure model hopefully is good enough. One of the many that uses this model is SWIM. And SWIM is the protocol that we use underlying Consul. And we evaluated a lot of different technologies before picking SWIM. It was first brought out at an IEEE DSN conference in 2002. And it actually says very clearly in the paper that the crash failure is the expected model in this domain, and of course, therefore, they support the crash failure model. So SWIM is on board with doing things the kind of realistic way. So when we evaluated SWIM for our own use and for your use indirectly, there were a bunch of criteria. We knew that we needed something that scaled. We wanted it to be robust, both to network problems and local node problems. Again, there's no point having an unreliable failure detection system. And we wanted it to be easy to deploy and manage. And it turns out SWIM has some really nice properties. The way it's architected actually really helps with this stuff. It's a peer-to-peer system. Consul has servers, but not for SWIM. The SWIM part is down in the agent. So a Consul server also happens to have the agent running. So from that perspective, it's just another one of the members of this group. So this is completely symmetric. There's no special nodes to administer. There's no special nodes to worry about recovering from when they fail. And it uses randomized communication. This is really nice. It means that you don't have the chance of a correlated failure is much lower. Each round of communication, each node is picking some random other member of the group to communicate with. And this sort of gives a really good strength to the patterns of communication. We'll come back to that a little bit later. And within that communication, it's using gossip. It's not the case that one node has to talk to all the other nodes, or even 10% of the other nodes in a certain amount of time. When information is passed from one node to another, it's the sort of epidemic or viral model, the contagion model. Information spreads through the network by hops, and there's been a lot of theoretical work done on this. Now, to be clear, this is probabilistic. So, you can have that perfect storm where once in a while somebody doesn't get that message for a certain amount for quite a long time. We have extended SWIM. We have some direct sync that we put in periodically between nodes, which encourages this to converge a lot faster, and we have a hard upper limit. But in the general case, there's actually a simulator on our website where you can see how quickly it converges. And even in order of thousands to 10,000 nodes, the convergence is very fast. So, SWIM is mostly excellent. We've been using SWIM for, I think, 5 years now, and we've grown as the community has grown. The scale that people are using this at, I think early on, it was of the order of tens or hundreds of machines. Then we start to hear about people doing thousands of machines. Then we start to take a little survey, and we find there are plenty of big users routinely deploying a single Consul group of more than 6,000 machines. And just in the last few months, I'm now hearing 10,000 machines. So this thing scales really well. We also use it directly. You can, of course, use Consul and do use Consul to build the availability and, for your services. But we also directly bake the SWIM implementation into Serf and Nomad directly. So all three of them share the same library. It's called MemberList. It's a HashiCorp open source library. However, while it is generally excellent, there are occasions where users would come to us, sometimes a little bit panicked, where there would be a kind of escalation. Hey, we really need your help. We've got this weird situation. Help us out. So over a period of time, there were a number of debug sessions, and a picture started to emerge of what the problem was. So here I'm going to use a distributed denial of service attack to motivate the problem. But generally speaking, there's the whole class of problems, and I'll point that out in a second. But so here we are. We've got that same cluster, and you have some edge nodes, which are responsible for the ingress and egress. Maybe they're running firewalls, load balancers, web servers, whatever the right thing is in this particular environment. And they're getting hammered by a distributed denial of service attack. So, OK, fair enough. We expect some of these nodes to fail. They're overloaded. But the peculiar behavior is that in addition to that, we see some flapping nodes. And these nodes are not actually directly under attack. These are nodes in the interior of the cluster that shouldn't be being affected. So what do I mean by flapping? So this is a healthy node. These paler colored ones here, they're healthy. They're being marked as failed by Consul. And then a little while later, they're coming back and being marked. So they're being marked as failed, and then they're immediately being marked as healthy again. If you would go in and look at the logs for that instance, you'd see no problem. There's plenty of CPU, there's plenty of network connectivity. It's not under attack. Even more disturbingly, other healthy nodes think this healthy node is sick. So what is going on here? This is not cool. And as I say, the DDoS is a concrete example, but we got this in a few different ways. Web servers were overloaded, video transcode servers. It doesn't have to be on the edge. It can be in the interior of your network. Somebody is using these burstable instances, the AWS T2 micro instance, where on average it's not allowed to exceed 10% of its CPU budget. So you can do a burst of work, but then the budget is depleted. Eventually, if you go to zero budget, you're throttled. So the common thing here is that there's some resource depletion, whether it's typically CPU, sometimes network, but there's resource depletion at some nodes, and it's making other healthy nodes appear unhealthy. So this was the mystery, and we dug in, and we have a nice solution. And on Thursday, I will be in Luxembourg presenting this at DSN, which is very nice. This is the conference where SWIM was originally published, and it's really nice to come back there. And we've been in communication with Indranil Gupta, the lead author of SWIM, and he likes this work and is very happy that we've done it. So yay. I'm not going to go over this in detail. You could watch the talk I gave at HashiCorp last year if you want the details of this. I also recommend you read the white paper, which is on the archive website, freely available. And it gives all the details. But to talk about what I am going to talk about today, I have to just give you a little high-level summary of what was wrong. So I'll give you a very quick description of SWIM. All you have to know here is that SWIM is a protocol, distributed systems protocol. It has a number of steps. In step 1, Node A directly probes Node B. It's trying to say, hey, are you alive? It sends it a ping or a probe. If it gets back a response within a timeout, great, you're OK. I move on. If not, denoted by the X, we move on to step 2, and we say, OK, I couldn't talk to you directly. Let me just see if it's a connectivity problem between you and me. Let's go around. I'm going to ask these guys to talk to you. So then that's a probe request. They make the probe. If they get through, it comes back to you. OK, I'm still happy. If it doesn't come through, then we move on and we start gossiping these rumors. Hey, I think that guy's dead. And it's, we're going downhill at this point. Interestingly, in the SWIM paper, now 2002, Cornell University, Ivy League school, 55 computers. They thank Werner Vogels, CTO of Amazon, of AWS. At the time he was a professor there, he helped them get 55 computers together. This is large-scale distributed systems at a university in 2002. It's amazing how well this thing works, given that that's the only scale. I mean, we had people take this way past 1,000 machines before they really started to hurt with this problem. But even then, at 55 nodes, they had this thing that they saw, which is sometimes they would get these false positives, or they would get lots of false positives. And they tracked it down, and it was because sometimes a message isn't processed fast enough. There's slow message processing. So they put another mechanism. I'm not going to give you the details, but they had a way to sort of give people longer to come back and work around this. What we discovered was that, unfortunately, even that remediation, this suspicion mechanism, even that has the same vulnerability. It still requires some of the messages to be processed in a timely manner. So the problem we have here is Node A was suspecting that Node B was dead, and it gossiped this rumor. It said, hey, I think you're dead. And what the suspicion mechanism is good at is, like, Node D here is actually dead. Node D couldn't help. But the epidemic nature of the suspicion mechanism, it floods around any slow or dead nodes. If there's a fast way to get the information from A to B, it will get there. And if there's a fast way to get it back, it will get it back. Unfortunately, if the node that was asking in the first place is also slow, the message can even be in the computer. It can have come into the kernel. It can be somewhere in a device driver or the protocol buffer, or even in a Go message queue. It just hasn't been processed yet, and the timeout comes. So there's this sort of fundamental, this is the exhaust port to their Death Star. There's the flaw that, unfortunately, they were not able to patch. And we have plenty of users who ran into this at scale. So generally, our approach to fixing this is we realized that there are all these messages. We know the protocol. We implement the protocol. So when we send a message, there's an expectation. We know whether we should receive a reply. And it's just some basic accounting. You sort of keep track of, well, I've sent 3 messages out in the last 200 milliseconds. I really should get 3 replies back in the next 500 milliseconds. And because of that fully randomized communication, you're very well connected to the whole network. And it makes it's possible that you got unlucky and you talked to 3 dead guys. It's possible, but much less likely than that you are becoming disconnected from the network, unless your whole data center is going down, and then you have some other problems to worry about. So, and actually, it's robust even to more than 50% of the nodes going out. So, but basically, what we're saying is, we know we have an expectation of how many messages I should receive, and now, if I'm isolated, even the absence of messages, absence of replies is a signal to me. And that's nice. You know, it means that you can be completely isolated. You can be disconnected from the network. And you know, hey, I should slow down here. I should give these other people more time to reply to me. Then it's an intermittent problem. You get some packets, or you're bouncing along with the CPU throttling. You're going to give other people the benefit of the doubt. And this works really nicely. So the false positives were the problem. All these nodes being accused of being dead when they weren't. And there are three components to the solution. So on the left, you have without any of the components. On the right, you have the full solution of Lifeguard with all three components. And in the middle, just for interest, the impact of each of them. And when you combine them all, each of them has an effect, but when you combine them, there's a sort of synergy. At each stage of that pipeline, we're knocking down the false positives. And it's really powerful. And once this was deployed, those kind of support requests stopped. So it's a good thing. Also, something really cool, we found that you can tune the parameters of swim. Now that we have kind of got those bad guys out of the way, we can actually be more aggressive. So there's a knob. You can basically choose median latencies. On average, how long will it take to detect a failure? How long before a healthy node sees that an unhealthy node or a dead node has died? You can choose to leave that where it was and be really aggressive, have more than a 50x reduction, down to 1.9% of the false positives, or you can balance it. You can say, you know what, I'll just take a 20x, 25x reduction in a 20x reduction in the false positives, but I'll take a 15x reduction in the latency in the healthy case. So this was an unexpected bonus, a nice side effect of the work. We weren't looking for this, but that's cool. We were able to tune the system more aggressively because we've eliminated a class of fault. All right, so mission accomplished, right? We go home and we move on to the next project. Well, maybe not, because why did this happen? How did we get into this situation? We want to understand this fundamentally. And it turns out SWIM is in a line of work. If you go back to 1996, back at this time, people were worried a lot about multicast and virtual synchrony, delivering the messages to everybody simultaneously. It's a different era from this was not the cloud era, but a very important paper came out talking about unreliable failure detectors. And so the notion of an unreliable failure detector, there's going to be these processes, they're monitoring one another. Hopefully there's some redundancy to that monitoring to make sure that when somebody fails who's monitoring somebody else, we're still doing the monitoring. There's a whole raft of ways that this can be implemented. This is not tied to whether you're using heartbeats or tokens in a ring or doing the probes that SWIM does. These are all alternatives, but this is an abstract model of a failure detector. And again, different topologies with the rings and hierarchy, with the randomization. This is what SWIM uses. But the key point is that each individual failure detector can be unreliable. It can have false positives. And then you overlay a protocol on top of this, which filters out the false positives. So SWIM fits into this. SWIM is an instance of an unreliable failure detector. Now, within this abstract model, there's the concept of a local failure detector module. So practically speaking, this is the member list part of Consul agent. We said that we have a group of processes, that's their generic term, who are monitoring one another. Each of those processes embedded within it or co-located, doesn't really matter whether it doesn't have to be the same process, but on the box, hopefully exposed to the same conditions so that it's kind of a proxy. The failure detector on each one monitoring some of its peers. And in the first instance, when this work was published, it was all about really thinking about the far end. It was thinking about, is that guy alive, is that guy alive, is that guy alive, sending these probes or heartbeats or however you wanted to do it. Over time, people realized that the characteristics of the network were kind of a form of interference. So they started to develop more fancy models where you could actually, over time, learn a model for the behavior of the network, and then maybe you sort of subtract that. So you denoise. You take a filter to remove some of the bias that you're seeing. False positives you might accuse, or you may not wait long enough for process B because of some network problems that you actually could figure out were occurring because you saw how the time of the heartbeats was degrading in the last 20 seconds or something. Many, many works following up on this. So many publications followed this. So we read them all. And not a single one has talked about the health of the actual failure detector itself, of this local module. They're all focused on the far end Some of them get into this nice modeling of the network, and in the case of SWIM, the suspicion mechanism. We're worrying about the peers in between who are forwarding the messages. It seems to be a blind spot. It's kind of interesting that we've gone on so long without people paying attention to this. And you have to think it's probably just a side effect of supporting the crash failure model. In this world, you're either alive or you're dead. So why would I care about your health? If the failure detector's working, there's no problem. If it's not working, it's gone. So fundamentally, it's interesting how the whole community can adopt the same path for 20 years. So we're now, wondering what is the scope of this thing, this local health, and for the first time potentially worrying about the health of the local detector. Where does this fit in? I mean, we were reading these papers because we surely were going to bump into, somebody must have done this before, and we could cite them. And we get to find it. But some good news came. In parallel to us working on this and publishing there's an awesome workshop called HotOS. It's out of the ACM, Association of Computing Machinery. And it's a really cool venue. People just write these short workshop papers, but they're sort of talking about the big, painful problems. They're trying to find the next big research topic that the community should move towards. And there's a lot of great work. You can see that the seed of the idea shows up at this workshop. And last year was no exception. A fantastic paper. I would urge you to go and read the Gray Failures paper. This is a report from Microsoft, and crucially, you'll see there's Microsoft Research and Microsoft Azure. So this is not just the boffins over there in the ivory tower. It's research and engineering working. And the people, I know these people in research. These are people who have helped to build Bing and Azure. They're not ivory tower researchers anyway. These are people who've led development teams. So this is the considered opinion of people who have been intimately involved in building one of the largest private and public cloud infrastructures. And their definition of a Gray failure, and they're not, they're saying, look, this idea's been out here for a long time, but they're now shining a spotlight on it. They say, things don't always fail cleanly. There are these gray cases, and it can be to do with some degraded hardware. And the thing can limp along. It's not dead, but it's not happy. And these are exactly the kind of conditions that induce the problem that caused us to build Lifeguard. And they even call out, that this model is overly simple. Interestingly, you'll see that they call it fail-stop. The definition is actually crash failure, and they misname it. So, even these people are using these terms a little bit loosely. There might be a clue here to what's going on. But they definitely nail the cause. And the cause really is scale and complexity. And actually, there's a quote. I love this. It's pretty much the definition of the data center, where the unlikely becomes commonplace. So we talk about some, PCI bus controller malfunction or some cosmic ray or whatever it is. These are like 1 in 100 million type things, maybe, or 1 in 10 million, whatever it is. When you have a room with several 100,000 machines in it, multiple of these issues are always going to be going on somewhere in that room. So the good news is, congratulations, we've made it to Google scale problems. You and through you, us, we are now having to wrestle with these same problems that Microsoft and Google. We're using their infrastructure, and they can't isolate us from all of these problems. So we've got their scale of problems. So I guess that's good news. This actually came from another really good paper, Visigoth from Eurosys. Not going to have time to go into this. I would also encourage you to read this paper. These guys are trying to take the Byzantine fault tolerance and make it really usable. They have a particular programming model you have to use, which does limit the applicability. Also, they are trying to leverage how reliable, in terms of performance, modern data center networks are, but I think that public cloud is, this is something that could work for Microsoft, provided they're running it on their latest gen switches, not so much if you're in random public cloud. So that's why we're not dwelling on this, but this is a great paper, and we honestly are still unpacking the thoughts that are in this paper, and we may end up implementing some of the ideas from here eventually. So now we have the concept of a Gray failure. As I mentioned, it strikes us that local health really is something that could be helpful here. We've applied it to Swim. Now, Swim's kind of the easy case. I told you about that fully randomized communication. This is great. You're very well connected to everybody in the data center. You have a really lot of good signals to the fact that you are either well connected or not well connected. Heartbeat failure detectors, it's more point to point. Then the rings in the hierarchy, there's a bit more. There's going to be some redundancy. We think this could be applied, so this is a future research area for us and hopefully for other people. But the criticism could be, it's only going to be robust with Swim. You're not going to make it work with heartbeat failure detectors. Interesting thing here is that, usually you will have multiple heartbeat detectors co-located because you want that redundancy. Everyone is checking a few other people. In the literature, they never think about the co-location. They never cross a signal between the different instances because they had no need to. It was always healthy. But now we think about it having poor health. I have 5 failure detectors co-located. Maybe I can look at the correlation. If they all stop getting their heartbeats, maybe it's me. Also, you could actually do the Swim-style randomized probing. Even if you send one message from one node each second, that's going to give you some background level of confidence that there's communication. And also, if you want network coordinates, in Consul we have Vivaldi, which allows you to, say, route me to the fastest, closest instance. You could do that. So there's a value add to having some sort of background radiation, 1-second messages between peers. There was another really cool paper at HotOS, this time from Google. I don't know if they talked to each other first, but Google and Microsoft show up at the same conference and start talking about the pain points that they're having at scale. And the most important thing that they brought to the table here is it's common sense, but sometimes you need to be reminded of the obvious, that there's this inexorable link between availability and performance. Is it dead, or is it just running really, really slowly? And we seem to be having some trouble with things that are running really, really slowly, so let's maybe model this as a performance problem. OK, but still, how did we get here? Why is it in 2017 that we've got Google and Microsoft showing up at the same conference saying, you know what? We've been doing this fail-stop thing for a while now, and it's just kind of not working for us. And confusing fail-stop with crash-stop in their terminology. So how did we get here? And I told you about Stefan's course, and the link is on Twitter. He's actually been teaching this course for 20 years. It's based on his PhD thesis, which you can buy as a book. And what community is he in? He's doing real-time systems for automotive. He's doing hardware and software co-design. He's trying to build dependable systems. And it turns out, if you go to IEEE DSN, Dependable and Secure Networks is what DSN stands for, it turns out that in that community, this is a problem that has been considered as an electrical engineering kind of a hard hat. This is for trains and missiles and chemical plants. There are lives at stake. These people are taking this stuff incredibly seriously. This is an awesome paper. I encourage everybody to read this paper. It's just a fantastic, very detailed, very precise enumeration of all the aspects of building a dependable system from the point of view of engineers with a capital E, not software cowboys. And there are just some amazing diagrams in here. Here it is. Basically, not every failure is a stopping failure. There are these erratic services. Oh yeah, 1980. They started classifying this taxonomy in 1980. It's all laid out there. Google got the message last year. But stopping is a strategy. This fail-stop thing, yeah, it's really hard, but guess what? You actually commit to doing that. You try to make your systems fail. You're failing safe. It's the dead man switch, where the driver has a heart attack, he lets go of the handle, and the train stops. They had to build that. That doesn't just happen. So this is some pretty important stuff that doesn't seem to be present in our community. So what can we do? Actually, I'm going to go straight to this one. I have a general prescription, which you can guess from the last couple of slides here. I really think we need to start thinking in terms of building dependable systems as a design center. We've taken the terminology, fail stop, crash stop. We've gone over there to the IEEE guys, and we said, oh yeah, that's a great model. Yeah, thanks. And then we've done absolutely nothing with taking their practices. And of course, we're in a different setting. We're not doing hardware and software co-design right now, although if you look at SDN and disaggregation in the data center, people are starting to say, if we had this switch that has these special hardware qualities, maybe, so we could actually go in the direction of hardware and software co-design with this stuff. But even without that, concretely today, We have to go beyond the binary and generic. I mean, we're seeing it now. Is it alive or is it dead, or is it just running slowly? Google pointed the same thing out, but people have been doing this. You have to set the SLAs, you have to set the quality of service, you have to think about the application level view of the health of your system. Is it delivering at the rate that it needs to deliver to be considered a happy, healthy, active member of this population? And if not, we should flip the script. We should say, okay, I'm not going to let him run until I'm sure he's dead. I'm going to kill him. It's time to go. Or local health, it kills itself. So these are my prescriptions. I hope some of this has sparked some thoughts for you. All of the references are on Twitter, and I'd love to talk to people about this. Thank you.